Welcome to Crashcast Java, where we dive deep into Java concepts to help you become a better developer. I'm Victor, and today we're joined by our expert Sheila to discuss the Java memory model and its impact on concurrency. Sheila, can you give us a brief introduction to this topic?
Absolutely, Victor. The Java memory model, or JMM for short, is a crucial aspect of Java that defines how threads interact with memory in a multi-threaded environment. It's essential for understanding how concurrent programs behave and for writing thread-safe code.
That sounds important. Can you break it down for our listeners who might be new to this concept?
Of course. Think of the JMM as the rules of a multi-cook kitchen. Each cook or thread has their own workspace, local memory. But they're all working in the same kitchen, shared memory. The JMM defines how changes made by one cook become visible to others.
That's a great analogy. So, how does this relate to concurrency in Java?
Well, in concurrent programming, multiple threads are executing simultaneously. Without proper management, this can lead to issues like race conditions or inconsistent views of shared data. The JMM provides guarantees about when changes made by one thread become visible to others, which is crucial for writing correct concurrent programs.
I see. You mentioned something called the happens before relationship earlier. Can you elaborate on that?
Certainly. The happens before relationship is a key concept in the JMM. It ensures that the effects of one operation are visible to another operation. For example, if action A happens before action B, then the results of A are guaranteed to be visible to B. This is crucial for understanding how Java orders operations across threads.
That makes sense. Are there any specific language features that developers should be aware of when dealing with the JMM?
Absolutely. One important feature is the volatile keyword. When a variable is declared volatile, it tells the JVM that this variable might be accessed by multiple threads. This ensures that any read of the variable will see the most recently written value, regardless of cache states.
Interesting. How does synchronization play into this?
Synchronization is another crucial aspect. When you use the synchronized keyword or lock objects, you're not just preventing concurrent access, you're also creating memory barriers. These barriers ensure that all writes made by a thread before releasing a lock are visible to any thread acquiring that lock afterwards.
This all sounds quite complex. Are there common pitfalls that developers should watch out for?
Definitely. One common issue is assuming that operations are atomic when they're not. For example, the bar++1 operator isn't atomic, which can lead to race conditions. Another pitfall is relying on the order of operations without proper synchronization, which can lead to unexpected results due to instruction reordering by the JVM or CPU.
Those are great points. What would you say are some best practices for working with the JMM?
Some key best practices include always synchronizing access to shared mutable state, preferring higher-level concurrency utilities like Java, util.concurrent classes over low-level synchronization, and being cautious with double-checked locking patterns. It's also crucial to thoroughly understand the implications of the volatile keyword and use it judiciously.
Thank you, Sheila. This has been incredibly informative. To wrap up, could you mention a few advanced topics that our listeners might want to explore further?
Certainly, Victor. For those wanting to dive deeper, I'd recommend looking into 1. The Java util.concurrent atomic package for lock-free thread-safe programming. 2. The concept of memory barriers and their low-level implications. 3. The Java 9 plus varhandle API for fine-grained control over memory ordering effects.
Excellent suggestions, Sheila. And that brings us to the end of today's episode. Thanks to all our listeners for tuning in to Crashcast Java. If you found this episode helpful, please subscribe for more deep dives into Java concepts. Until next time, happy coding.